This video is the introduction to solids, which is the equilibrium of a deformable body. So before this, we only talked statics, and statics is finding the external forces and the reaction forces of supports on a member. But technically, there's more forces than just that going on a member. Technically, if you put a load onto a member, the member either breaks or holds the load. And what determines that comes down to the internal forces that's going on within the member. If the internal forces didn't exist, the member would just collapse. So effectively, solids is going to be internal forces. And how we figure out those forces is by making an imaginary cut along a beam. And so our beam now being cut into two pieces, we're going to have both a left half and a right half of this beam. So we're going to have two pieces of this wonderful beam, one on each side, and now we're going to talk about how these internal forces actually appear. So again, we're going to make our cut right here on each side. So effectively, those are the two halves, the left and the right half of our member. And how it's going to work is effectively like a fixed end in statics, because effectively the left half and the right half are glued together and creating some type of a fixed end. Anything that happens on the right also happens on the left, but in equal and opposite fashion, else our little member would be in a whole bunch of turmoil and not very stationary, and that just wouldn't work. So now let's talk about our positive sign convention. Positive sign convention for this is a little bit different from what you would have had in the past. In the past, usually when we say positive sign convention, we're only talking about the equations of equilibrium, and for that we're just picking an arbitrary direction and just saying, for the purposes of summing things, we have to figure out which ones would be positive and which would be negative, so we just arbitrarily picked this direction as positive. But moving on now, when we're talking internal forces, we have to actually have a set standard for positive sign convention. And it'll make sense here in just a second, because technically they're equal and opposite, right? Otherwise they would not be in a state of equilibrium. So we start off with, for a fixed end, we have three directions. We have the x direction, the y direction, and moments. So our x direction force, what we consider to be positive, is going away from the face. Away from the face. And we call that x direction force N. And N stands for normal force. Or we also like to call this our axial force. And this force acts perpendicular to our imaginary cut. Remember, we're not ever actually cutting this beam. It's all fake. So there we go. We have our normal axial force, and it acts away from the face. So you can see they're different directions, so we can't exactly say, ooh, everything going to the right is always positive. So it doesn't really work when you're on the right side free body diagram. Next up, we also have our y direction, and our y direction, usually we like it to go up, but sadly on the left side, it's going to start by going down. Yes, so down, and it's called V. And then it's going up on the right, and again it's V, and V stands for the shear force. So that's what this is. This is a shear force, and that one's actually going to be parallel to our cut. Now in a 3D sense, you're actually going to have multiple shear directions, because you can have, a 2D face now. So you will have multiple directions for shear force, but we're going to mainly focus on the 2D for these videos. And lastly, what we have is the moment. And the moment is going to be going counterclockwise when you're on the left half, and clockwise when you're on the other half. So lastly, we have M, which again is just bending moment, and that's not changing in the slightest. So those now are our forces. Remember that that's the positive sign convention for it, and they're equal and opposite, as you can see, else the member would not be in a state of equilibrium. So how would you solve for these forces? Well, obviously the exact same way that you do in statics. You just sum the forces in the x direction, sum the forces in the y direction, and sum some moments about a point. Which point would you take to sum the moments? Usually, we always take the point that is the cut. That is just the easiest, because then you don't have to worry about your shear force that you just calculated creating a moment, because if it did, and you calculated your shear wrong, then obviously your moment's going to be wrong as well. So we like to take it about the cut just to prevent some error compounding for us. So let's see it in action. We've got an example here that we're going to work through. So here we have a beam. It's a 10-foot long beam. We have a roller on the left side. We're going to call that A. We have a pin towards the middle. It's not really in the middle. It's 6 feet from the left. It's 4 feet from the right. And that pin we're going to call B. And from the roller that's on the far left side, we're going to go over 4 feet. And we're going to have a uniformly distributed load across those 4 feet. And that's a 2 kip per foot uniformly distributed load. And then way over at the right side of our beam, we have a 10 kip force going down. Now, obviously, that's currently nothing special. Solving this problem right now, you'd just be solving for the reaction forces of A and B, and that's just statics. So again, solids is the internal forces, so we have to pick a point that we actually want to find the internal forces at. And the point that we're going to do that is C, and C is, again, it's 2 feet from the right of B. So we want to find the internal forces at C. Now there's a couple ways of going about doing this. Obviously we do have to make a cut at C to figure out what the internal forces are, but the real question becomes, which side do you take the cut? As you can obviously tell, we can do both the right or the left, and either one of them should get you the exact same answer. Now, you only have this choice because the problem statement does not distinctly tell you which side you need to find the internal forces on. If it specifically says, hey, I need you to find it just to the left or just to the right, then obviously you have to take that side's free body diagram. But in this case, you have an option, which sounds really cool. And there is what I like to call a correct and an incorrect option, but both of them will get you the exact same answer. The difference is one of them is going to take a lot longer than the other one, but it doesn't necessarily make it any worse, unless you just consider the loss of time to be terrible. So step number 1 usually is to find the reaction forces, but depending on which side you take, you may or may not need to do that. So hopefully at this point you're kind of getting the hint about which side would be the better side to do for the internal forces, but yep, we're going to start off with the terrible one. So let's start by finding our reaction forces. So here on this diagram, I have drawn out our reaction forces for us. Our roller only has one going up, and our pin has both an X and a Y component. And there's our beam all over again. So what we can start with is by summing the forces in the X direction and set it equal to 0. And you will find that there is actually only one force in the X direction, and that is actually Bx. Cool, so I guess Bx is equal to 0. At this point, what I like to do is I like to come back through and actually draw them, but it's kind of like a waste of ink if you sit here and redraw the 0, but sure, let's just leave it there, for that's where it's located. Next, we can sum forces in the Y direction, but of course we have 2 different unknowns there, so maybe not the greatest idea. So let's skip that one for now, and let's move on to summing the moments about a point. Technically, you could do it about any point, but obviously some points are better than others. And just to make this easier for ourselves, we're going to sum moments about A and set it equal to 0. Now, I like to always take my counterclockwise to be positive. You don't have to do that. Again, you can do whatever you want. The sign convention for this specific equation is only here to figure out which you're going to call a positive and negative, so that at the end of the equation, you can say either the answer was positive, which means you drew the arrow in the correct direction for that force, or if it's negative, all it means is that the direction that you originally drew it is incorrect. That's all it means. So, but I like to take mine counterclockwise, so that's what we're going to do. And I like to work all the way from the left to the right. So that way I don't miss anybody here. And obviously AY is not going to create a moment about A because he is acting at A. So next up we have this uniformly distributed load here. So what we need to do is break it down into a point load, and his point load is going to act right at the center. So that force, first up, we need to figure out positive or negative. Always a really good thing to find, positive or negative. So of course, if you draw the arrow for where the force would be concentrated, and then just see, is that going to rotate positively or negatively about? I like to draw an arrow and then look, does that match the direction that I assume positive or not? In this case, it does not. So of course, our 2 kip per foot force here is going to actually be negative. So we have a negative 2 kips per foot, and that's going to act across 4 feet. And that's going to bring us down to a kip force. Again, that's not a moment. We do need force times distance. And of course, it again is acting in the middle. So the middle of 4 feet here is going to be 4 feet divided by 2 to get all the way over to A. So that's awesome. There's the first one down. Moving over to the side, technically there is BX, but BX does not create a moment about A as it is in line with A. And then there's BY. Is BY positive or negative for this equation? Let's draw an arrow as it goes around A. And that is, in fact, in my positive direction. So I've got plus BY times the distance over to A, which is going to be 6 feet. Then there's point C, but point C, again, he doesn't actually have any forces on him externally, so we're going to totally ignore him. And then we make it all the way over to the right, and we see the 10 kip force, and the 10 kip force going down here is going to, if we draw our arrow, going to be negative as it goes around A. So we have minus our 10 kip force times the distance all the way to A, which is 6 feet plus 4 feet for a grand total of 10 feet. So there we go. We got kip feet, and we got kip feet. So cool. So what we're left with is BY here. You can go and solve for that, and you're going to get BY is 19.33 kips. And because it is positive, it does mean that the answer that we have for our arrow, the correct way we drew it, is actually going to be up. Because again, it was a positive answer, so that means that we drew it in the right direction. So I'm going to come back over here. I'm going to erase BY and just write in that this is 19.33 kips. Kind of keeping everything updated there. And now that we see that, we know that there's only one other thing to do, and that is sum the forces in the y direction and set it equal to 0 to solve to get AY. So again, AY is the first thing on the left there, and currently he's going up, so that's going to be positive AY. Then we have our 2 kips per foot here going down, so minus 2 kips per foot. That's kips per feet. We only want it in kips, so we do need to multiply by its distance across 4 feet. Then we have BY. BY was going up, so plus the 19.33 kips. Lastly, all the way at the end, we have a minus 10 kips going down. So what we do actually discover when we solve for this is that AY is equal to a negative 1.33 kips. Again, all that the negative means, technically you could go through and write the negative if you don't want to update every single free body diagram that you drew. But all that the negative means is that actually this is 1.33 kips going down instead of up. Now technically there's only one free body diagram at this time, so I'm just going to erase that completely and redraw that in its correct direction. So it's down 1.33 kips. So again, all we've done up to this point is statics. Yes, we actually have to do statics first so that we can set up our problem so that we can actually do solids. So now we're going to make a cut at C. And again, there is an obvious correct answer if you want to go quickly, or incorrect if you don't mind the slow route. But we are going to do it in both ways just to show you that they do get you the exact same answer. So long way first. And if you haven't already figured that out, yes, that's going to be the left side. So at this time, what we're going to do is we're going to redraw our free body diagram. It doesn't really have to be to scale. It's kind of a waste to draw them humongous, honestly. So here we go. We have our 2 kip per foot downward force. Technically, we have AY going down 1.33 kips. We have our BY going up, and that was 19.33 kips. And then at point C, we have our normal, and again, this is a left side free body diagram, so let's go up to the top and remind ourselves. Normal, our X force, is going to go outward from the face, shear is going to go down, and bending moment is going to go counterclockwise. So again, we have our normal force going out from the face, we have our shear force going down, and we have our bending moment, probably shouldn't have cut through that end, but whatever, going counterclockwise. It's definitely good to put distances on this. That'd be a great idea. So we've got 2 feet from the BY over to the cut. It's 6 feet from A to B, and 4 feet is the length of our distributed loads. Just to highlight through some things here, 4 feet is this distance. Then we've got 6 feet, which is this distance. And we've got 2 feet, which is this distance. So there we go. So again, how do you solve for these forces? It is just as simple as the same way you did it just a second ago. Yep, it's just sum of the forces in the X, the Y, and the moment's about a point. So let's start first with sum of the forces in the X direction and set it equal to 0. We didn't actually draw in lovely BX. Maybe we should have, but I mean, he's 0. So technically the only thing that we actually have, we just need to pick a direction positive, we'll say that, is just N. Yep, that's legitimately it, just N. So our normal force is 0. Now technically our directions don't really have a very typical fashion that we like to call them, because you can't just say, ooh, it's going over to the right, because on the other side it's definitely not. So when we're looking at our answer blanks over here for normal, shear, and moment, if it was a value that wasn't 0 and it was positive, then you would say that that's in tension, and we'd put a little parenthesis with the T saying that it is going always out from the face. So pulling it in tension is a positive. And if it was a negative number, we would come back and put in parentheses a C for compression. So squishing the member is compression, and that's negative, and pulling the member apart is tension, and that's positive. So when you are doing your normal answers, you do want to put either tension or compression so everybody knows which direction they're going. But for shear and moment, they're a little bit different. Now, unlike when we were doing the problem before to find the reaction forces, technically you only have the 3 unknowns, the shear, the normal, and the moment. So technically you can just do them in whatever order you want. So we can sum forces in the Y direction now, set it equal to 0. Usually for the equation though, we pick positive to be up. So this means that we are starting off very strong here with a minus 1.33 kips going down, because thanks AY. We also have another minus of 2 kips per foot for our uniformly distributed load, and that goes across 4 feet. Moving along, we have BY going up. That's plus 19.33 kips. And then lastly, at the very end, we do have our shear, and our shear is going down, so minus V. So when we do solve for this, we do get that V is equal to a positive value. It is positive 10 kips. So again, when you solve for this equation, the value that you get, positive or negative, is literally just telling you that the direction of the arrow that you drew for it to then incorporate it into this equation was either correct or incorrect. So positive that you're seeing here, this positive, just means that yes, in fact, the direction that you drew it, which was down, was the correct direction. Knowing that, and knowing that down on the left side is in fact the positive direction, that means that our answer is actually positive 10 kips. Okay, so it is kind of important to kind of watch what's going on there. But again, if you just draw it in the correct direction anyway, then the answer you see here is in fact the actual answer. Now lastly, we're going to sum the moments, and again we want to sum the moments about the cut and set it equal to 0. I like to choose counterclockwise to be positive, regardless of what side I'm on. So what we're going to have for this one is going to be, we have the 1.33. Let's draw some arrows, just see what that's going to give for us. So it's going to be going this way around, which is actually going to be positive. So we have our positive 1.33 kips times the distance all the way over to the cut is 6 feet plus 2 feet, that's 8 feet. Then we have our 2 kips per foot uniformly distributed force going down, which again is going to rotate it positively. Isn't this nice? So we're going to have this time positive 2 kips per foot across a total distance of 4 feet. And then the distance that this one is from its center over is going to be a little bit fun. We do have, it is 6 feet plus 2 feet, so that's 8 feet from the wall where A is all the way over, so then we have to minus 4 feet divided by 2. So yes, in total that is going to be 6 feet. But anyway, moving on. Next we've got our BY, and BY is going to be going this direction around, which we said negative. So this one's going to be minus our 19.33 kips times his distance of only 2 feet on over to the cut. And then lastly, we have our moment, M, and M is already in the positive direction. So yep, all that's left to do is add M. So there's our long equation for moment. Solving that, we're going to get that our moment is equal to a negative 20 kip feet. So again, what does negative mean? Negative does mean that our arrow's in the wrong direction. But if I drew it in the positive direction, then that does actually mean that our moment is a negative 20 kip feet. So that would be what we would write for the answers. And again, this was the quote-unquote long way to do things. It's long because, yes, you actually had to do all of these steps. You had to do a total of 6 equations to get the answer. Instead, what you could have done was way up here. You could have said, wow, why would I even solve for the reaction forces? If all I do is just cut this thing, I've got 10 kips going down. And then I've got my cut literally right here. This is 4 feet minus 2 feet in length, which is 2 feet. And we're looking at the right side. So we have a normal force coming out. We have a shear force going up. And we have a moment going clockwise. Ta-da! Free body diagram in just 2 seconds. Isn't that lovely? So now all you actually had to do was sum the forces in the X and realize that the only thing you have is technically just the normal force. So yet again, notice that our normal force was, yep, still 0. That's great. Probably shouldn't draw all over that. But anyway, next up, we're going to sum the forces in the Y direction and set it equal to 0. If I go left to right, the first thing that I have is my shear force. He's going up. Good job. And we usually like to assume up is positive for the sake of the directions on these equations. So shear's going up, so he's a positive value. And then we have the 10 kips going down at the end, so that's minus 10 kips. Lo and behold, when you solve for that, you get shear to be a positive 10 kip. And that is, again, the same answer. Wow. Like I said, they work. It's impressive. So lastly, we're going to sum the moments about the cut. Again, I like to take counterclockwise as positive for the sake of the equation. Going left to right, you're going to see, well, there is M in all of his glory, but he is going the wrong way for this. So we're going to have minus M, and then shear and normal are not going to create a moment about the cut, so all we have left is this 10 kip force going this way. which is negative as well. So we have minus 10 kips times a grand total of 2 feet, which who would have guessed it? Therefore, that means moment is in the easiest way humanly possible to see this, minus 20 kip feet. And as you can see again, the exact same answer. So there is, of course, an easy way and a hard way for everything. As you can see, it's not necessarily that difficult, but of course it does mean that if you do the wrong side, you probably have a lot more room for error, and you probably wasted a lot more time in your life. But regardless, you will come out with the same answer. So don't feel bad if you like the left one over the right one. That's okay. Whatever you want to do, you still work it out and you still get the same answer.